Good afternoon, everybody. Welcome to the Wednesday before Thanksgiving, Chem 170, with your host, me, Dr. White. If you look at the top, you can see, looks like it's just me alone today. Maybe some people are just running late, but I'll still do my lecture and lab today, and you'll be able to watch it on my YouTube channel. So let's go through some important things. Hang in there. Logging into D2L. All right, let me move this out of the way. Let me show you that I posted earlier this morning on Wednesday, test number 4, our last test before the final, test number 4 information. Next Wednesday on the 30th, I will be giving test number 4 online. And as always, you can download test number 4 password protected PDF file the day before, which will be Tuesday afternoon. And Wednesday, this coming Wednesday, a week from today, at 4 p.m. or earlier, more likely earlier, I will send out an email with the password for test number 4. You'll have until the next day, Thursday, 11 a.m., to finish test number 4 and upload your answers to the assignment area D2L. Please do it as a single PDF file like you've done all semester. Should take about 40 minutes to finish the actual test, but guess what? Because it's Thanksgiving, happy Thanksgiving. Take as long as you need to complete test number 4. Test number 4 will cover polymers, lipids, carbohydrates. Test number 4 has 9 pages, 20 problems. Some of the problems have multiple parts. Now, here's the points breakdown for test number 4. And there's 54 points. Yes, 54 points general knowledge, 15 nomenclature, and 36 reactions. Adds up to 105. So there's five bonus points. Now, nomenclature, you know from what we've done all semester, 2 types of problems. Here is the structure, give the name for it. And here's the name, draw the structure. And reactions, give the product or products. And I think I have 1 or 2, give the starting materials. Oh, what's this 54 points general knowledge? Whoa, it's never been that high. Well, here's why general knowledge is 54 points. If I say, is my right hand chiral or achiral? Well, that's not nomenclature. That's not reactions. Well, it must be general knowledge. By the way, it is chiral, non-superimposable mirror image. All right, and if I say, draw the enantiomer of this molecule, the mirror image, what is that? Well, it's not nomenclature. It's not reactions. So it must be general knowledge. And that's why general knowledge is a lot larger than normal on my test. And that's why it's 54 points. Oh, another one. Blueberry tea, always good on a cold afternoon. Actually, it's not that cold today, but it's always good. Uh, Another general knowledge question would be, what is white grease? Well, it's not nomenclature, it's not reactions, so it must be general knowledge. By the way, white grease is, and you should know, pig's fat. All right, now, this will not be an open notes test. None of mine are. On this Monday after Thanksgiving, this upcoming Monday next week, I will do my world famous review for the next test, which is test number 4. We'll have our regular Zoom meeting on Wednesday where I'll go through our, gosh, it's our last lab. Where has this semester gone? Wow, it's gone fast. Time flies when you're having fun with organic chemistry and Dr. White. And boy, did it. All right. Now, let me remind you, the extra credit project, 10 bonus points. The deadline is 11/30/22. Again, the deadline for the extra credit project is 11/30/22. And I highly recommend, well in advance of next Wednesday, if you're planning on doing this, email me your project. One of your colleagues has already done that. I'll check it. If there's anything wrong, I'll help you correct it. And remember, the bonus project is word, if you do it all right, 10. Yep, well, I do have 10 fingers. Oh, it's awful. Humor Wednesday. That was pretty awful. But 10 points. It's like getting 10 more points on one of your tests if you do it all right. Now, let me remind you, have a happy Thanksgiving holiday this weekend. I hope you get all the turkey or whatever your family serves. In my family, the turkey is not the only thing that gets stuffed. We all do. Oh, boy, do we get stuffed. And the best part of the turkey, my father loved it. He taught me to love it. I love it. And my he passed away a while ago, but my brother-in-law loved it. And that's the tail of the turkey. And in Yiddish, we call that the pupik. And that was the most fought over part of the turkey at our celebrations until we came to mutual agreement. Everybody gets an equal part, even though everybody look at, how come yours is bigger than mine? No, I would do the cutting and it would be equal. All right. Any questions? Well, no one's here, so there are no questions. If you do, before I do this, let me remind you, since today's tonight at 5 p.m., Elgin Community College officially closes. All offices, all classes, and any kind of teaching, what would be the right term? Anything associated teaching is closed. Good, I won't do that again. Anyways, closed, and therefore tonight I will not have office hours. All right, let's go to the lipids problem set. Now, you can tell it's the end of the semester because Dr. White's getting lazy. What's a lipid? See notes. Well, that's something isolated from a man, something that was alive, plant or animal or man, that's not soluble in polar things like water, but polar is soluble in nonpolar things. Name one type of lipid. Well, a lipid that's non-saponifiable would be a fat and oil, or I've got it backwards. A lipid that would be saponifiable would be a fat or an oil. A non-saponifiable lipid would be a steroid. Now, these are important things you should know. Hint, what's the difference between a fat and an oil? Well, fat is a solid or semi-solid at room temperature. For those of you who are wondering, room temperature is 25 degrees C. And an oil is a liquid at room temperature. And you should know, as I mentioned earlier, in general knowledge, hint, what's yellow grease? Pig's fat. What's white grease? I don't have it there. Pig's fat. What's tallow? Beef fat. And that's an industry for a number of years. I worked then, so I know it quite well. In fact, I worked at that time for one of the largest companies in the world that took animal fat to make fatty acids. All right, next one. Give the organic product or products for the following reaction. And if we look right here, what functional group do we have? Carbon, oxygen, carbonyl, R group. It's a ester. Actually, there's another one here and another one here. And we're reacting with sodium hydroxide and water. And for test 3, you learn ester, sodium hydroxide, and water, otherwise known as saponification of an ester, gives back the alcohol you would have used to make that ester, plus not the carboxylic acid you would have used to make that ester, but the carboxylate anion of that carboxylic acid you would have used to make that ester. Why? Because the carboxylic acid reacts with base to give the carboxylate anion. So ester number 1, this alcohol plus this carboxylate anion, the double bond will not react with sodium hydroxide and water. This ester, this alcohol plus this carboxylate anion, and the last one, this alcohol. So you get glycerin plus this carboxylate anion. Next, same molecule, if you're reacting with acid and water, under these conditions, this double bond will not react. By the way, this is the reaction that's going on in your body when you eat fats and oils, and that's acid hydrolysis of an ester. Remember, in your stomach, you have acid and water, and one of the miracles of life to me is I and you have cells that make hydrochloric acid, H+. And that's there to one of the reasons to break down the fats and oils, which are esters, to do acid hydrolysis of an ester, and you get the alcohol you would have used to make that ester and the carboxylic acid. So for this one, first ester, get this alcohol, this carboxylic acid. Remember, your friend for test number 4, like all semester. How many bonds to carbon? 4. How many bonds to carbon? 4. Do you break carbon-carbon single bonds? No. Do you break carbon-carbon single bonds? No. So remember that. That will be your friend next week when you take test number 4 and later in the future when you take my final. And it will always be your friends. So this is ester number 1, gives this alcohol plus this carboxylic acid. Ester number 2 gives this alcohol and this carboxylic acid. And ester number 3 gives this alcohol and this carboxylic acid. Now, let's look at the following. If you react this molecule with hydrogen and nickel, what will happen? Esters do not react with hydrogen and a catalyst, hydrogenation. I'll say that again in slow motion. Esters do not react with hydrogen and a catalyst. So these 3 esters won't. Oh, a double bond. And you know from test number 1, a double bond, 1 pi bond, 1 sigma bond reacts with hydrogen and catalyst. I don't have down there, but nickel, platinum, and palladium are the catalysts. You break the pi bond like that. Ooh, like that. They're not working. I got to get new batteries for these. That's better. Like that. And each carbon in a double bond gets a hydrogen. Well, this all comes along. The only change, you break the pi bond. Notice I was nice enough to say, look, and each carbon gets a hydrogen. This does not react because esters do not react with hydrogen and catalyst under these conditions. How do I know? Well, that's how all your hydrogenated fats and oils are made. Now, if you change the catalyst, you get the same thing. Now, let's look at E. Here we have what? Ooh, again, esters, and we're reacting with steam. Ooh, remember, steam is hot water, and one way to catalyze a reaction with water is use a acid or base catalyst, but another way to catalyze a reaction is, for many reactions, increase the reaction temperature. And if you use hot water, steam, especially high pressure steam, you are going to increase the reaction temperature greatly. And I worked for a company that did this reaction. I'll talk about it in a second, maybe 5 seconds. Take an ester, react it with steam, which is hot water. You get the same product as acid hydrolysis of an ester, the alcohol you would have used to make that ester, plus the carboxylic acid you would have used to make that ester. And the company I worked for, Unichem Chemicals, back when I worked, and it was located, I think they've been bought out by someone else. They still have their main plant at 47th and Racine in Chicago. We used to do this reaction to the tune about 2 to 3 million pounds of fat a week. Yep, 2 to 3 million pounds of fat a week. Yes, we made a lot of, you'll see when you do that, this ester gives you this alcohol plus this carboxylic acid. The double bond will not be changed, and you don't break carbon-carbon single bonds. Second ester gives you this alcohol plus this carboxylic acid, and the third ester gives you this alcohol and this carboxylic acid. And we did this reaction to the tune of a couple million pounds a week, and we made a couple million pounds a week of glycerin and fatty acids, which we sold. Now, let's take a look at F, yellow grease plus acid and water. What is that? Well, remember, my designation for yellow grease, tallow, and white grease is this, or R sub O is a sterile group, aminolale, R sub S is sterile. And this is my approximation in one molecule to make it easy for you to understand what's going on, what actually happens. And if you look at this, you get acid and water reacting with this triester. It's again acid hydrolysis of an ester. You get back the alcohol plus the carboxylic acid you would have used to make that. And in this case, you get 3 different products. First ester gives you this alcohol, plus this is an abbreviated way of writing stearic acid. If I ask on a test, draw the structure of stearic acid, don't use this, show all the carbons. But if in a problem is set up this way, you can use the abbreviation. Next, I have this ester, I get this alcohol. Notice R here is RO, so I'll get this fatty acid, which is oleic acid. And the third ester, I will get this alcohol, so I get glycerin. But notice the R group here in the carbonyl, R sub S, so I'll get stearic acid again. You want to put a 2 in front or write it down again, you can, but you don't have to. Notice you get three different products, glycerin, stearic acid, oleic acid. And I worked for Unichem, and we made glycerin, stearic acid, oleic acid. And we purified all 3 of these and sold them. Now, if you take tallow, the way I showed you, this is the same designation. So you're going to get the same as F. If you take white grease, guess what? Same structure, not designation, structure as F, and therefore you're going to get the same products if you're starting with this to make this. All right, let's take yellow grease and steam. Well, steam, hot water, you'll get back the alcohol plus the carboxylic acid you would have used to make that. which are the same products as acid hydrolysis of an ester, in this case of fat or oil. And therefore, you're going to get these again, glycerin, stearic acid, and oleic acid. And same thing with tallow, same structure. Now, if you take yellow grease and react it with sodium hydroxide, yellow grease has this structure, so does white grease and tallow for my class, and that's a triglyceride, 3 esters. If you take an ester, you learn for test 3, sodium hydroxide and water, you get back the alcohol plus the carboxylate anion you would have used to make that ester. Now, if we look here, yellow grease is this compound, sodium hydroxide and water. First ester, you get this alcohol plus this carboxylate anion, sodium stearate. This alcohol ester, you'll get this alcohol plus the R group is R sub O, you'll get sodium oleate. And the final ester, you'll get this alcohol. Notice the R group here is R sub S, and you'll get, again, sodium stearate. Now, do you have to put a 2 there, write it again? No, because I don't balance equations in this class. When we're just talking about what are you making, which is a lot what organic chemists do, especially in industry, you don't balance equations. So once again, you get 3 different products, glycerin, sodium stearate, sodium oleate. And if you start with white grease or tallow, you're going to get the same thing, because for my class, you'll use the same designation. And as I mentioned, well, I mentioned it, I'll mention it again. When I worked at Unichem, I was a laboratory manager, and I worked with the purchasing agent to make sure the millions of pounds of fats and oils we got each week met the quality we needed to make the quality products we were making. And we could interchange yellow grease, white grease, or tallow. You tried to have the purchasing agent, I and the president and my boss, vice president of production and research, we all pushed him to get as much, if he could get his hands on good quality yellow grease, white grease, pig's fat. Why? Because it was about 3 or 4 cents, sometimes even 5 cents a pound less than tallow. Tallow is always a higher price fat. And guess what? If you're buying 150 million pounds a year, and you can save 5 cents a pound, that's a lot of money. Hold on, there's a piece of dirt on top of my monitor. Get off my monitor. It did. And notice I have hidden all the way at the bottom, what is a surfactant? That's a molecule with a polar head, nonpolar tail, that interacts with different polarity materials to bring them together. And that's the end of the fats and oils or lipids practice problem. These are problems you should know how to do. And as you've learned all semester, that's why I call them practice problems, because they help you practice for my test, in this case, test number 4. All right. Make this a little bigger. All right, now, one of the things I didn't have on the practice problems for test number 4, and that's the following. You should know How does soap work? And you should know, if in my class, you should really know this. Hold on. Everybody get the hint? Know this. You should know the structure of soap. And soap has a nonpolar tail and a polar head. Example of that would be sodium stearate or sodium oleate, or the mixture, which is called in our industry, the fats and oils industry, sodium tallowate. And you'll find this in your bar soap. Now, the most important, let's think about this. Here's dirt. And you want to get it off your hand. How do you do that? Well, water won't do that. What's the key to this puzzle? I'll write it in red because then big, because it's so important. Like dissolves like. That means polar things are soluble in polar things, and nonpolar things are soluble in nonpolar things. And when you mix the two together, they're not soluble. Like if you take vegetable oil and water, it's not soluble, it separates. So you should remember water is polar. And dirt and grease are nonpolar, which is why water doesn't get it off your hands or other thing, water alone. Now, if you use soap and you're rubbing your hands like this, if you're washing your hands, like I did earlier today, the dirt on your hand is nonpolar. The soap has a nonpolar tail, which is attracted to that. The polar head wants to stay as far away from the dirt, but the tail is attracted to it. And I'm just showing but the whole piece of dirt is surrounded by the soap molecules to form what you should know is a micelle. Micelle is a dirt particle. In this case, there are other types of micelles when you talk about surfactants, but we're just talking about dirt and grease and soap. And here, the micelle now looks polar because the water only sees the outer polar heads. And water looks at the but you know water molecules have eyes. They don't, but it sounds good. And water looks at the micelle, sees a polar substance, and says, you know, water could talk. No, it can't, but it sounds good. Hey, micelle, you're polar, I'm polar. Let's go down the drain together. And they do. And that's how you get your hands clean. That's how you get your body and hair clean. That's how, if you're washing your dishes or your clothes, your car, or anything else, that's how, when you're using soap or detergent, it works. And this is something you should know. I'll go through it again. How does soap work? You should know. Soap has a nonpolar tail, polar head. Water is polar, dirt and grease are nonpolar. The key to the puzzle is like dissolves like, and you should know that. The key to the puzzle, how does soap work, is like dissolves like. It's so important. That's why I wrote it real big, and I wrote it in red. When I write something in red, that means it's real important. And you should know soap molecules, the tails are attracted to dirt, nonpolar, because they're like dissolves like, and forms a micelle. Excuse me. And I'm getting all choked up over this exciting stuff. And you should know a micelle, what's its structure and how to draw it. And finally, once you form it, water looks at a micelle and says, I'm polar, you're polar, let's go down the drain together. And they do. All right. So a couple other things I like to do before we do the lab. Not yesterday, Monday, I finished carbohydrates. But let's look at a couple of things important about carbohydrates. But let me remind you, on Monday, I will go through the carbohydrates problem set. Again, on Monday, I'll go through the carbohydrates problem set. Now, and since there's nobody I can do a thumbs up with, I can check now with new version. Good. Here is glucose. And I won't ask on test 4 what's the structure of glucose or fructose, but you should be familiar with it. And the question is, what's the product or products of this reaction? And the general reaction, if it were intermolecular with separate molecules reacting, would be an aldehyde or ketone plus an alcohol with acid catalyst gives you, keep your eye on the carbonyl carbon, what's attached to it, R prime or hydrogen, or an R double prime are still there. This has now OR and OH, and hemiacetal, hemiketal. Well, for this, here's our aldehyde, and on this carbon, C5, that's our alcohol. And just like this attacks that, this will attack the carbonyl carbon. And what's not involved in this reaction doesn't change. So I can redraw it. And I do. And now this carbon, which is this carbon, which is this carbon, will have a hydrogen, OH, and this bond right here from the alcohol will be from this hydrox group to the carbonyl. And there we go. And you should know this. If I give you this structure and this, and I ask what are the product or products, you should know how to get to here. If I give you this structure, with the double-headed arrow, what's the starting material, you should know how to get back to glucose. And this is fructose, the sweetest sugar in all of nature. And it's found in high fructose corn syrup that's in many of the products we now purchase. And once again, this is in equilibrium with another product. And the same reaction can and does occur. But here our prime is not hydrogen, it's carbons. And here's our carbonyl. I'll draw it in, but normally I wouldn't. And if we react it with an alcohol, now if it's between two separate molecules, intermolecular, you need an acid catalyst, and fructose you don't. And what's attached to the carbonyl carbon will still be attached. And you'll get this acid hemiketal in this case. Well, once again, here's our carbonyl. Let me get this up. This is our carbonyl, and this alcohol right here is this right here. And again, it's at carbon number 5. And just like this attacks here, this will attack right there. And what's not affected by this reaction, now this carbon is going to become this carbon, so I'll draw it. But the next 3 plus the CH2OH are not affected. And this oxygen is this oxygen, and our group is this, and it's bonded to this carbon, which is this carbon, and this will have a hydroxyl group. And you should know how to do this. If I give you this structure, you should know how to get to this. If I give you this structure as the product, you should know how to get back to the structure of fructose. And these are very important. Now, if I look at the clock, let's take a 5-minute break, and we'll come back and continue on. We'll do a few more things that are important from carbohydrates you should know, and then we'll do today's lab. And I'm going to take a 5-minute break. Well, that was a little more than 5 minutes, but I got some cool stuff in the mail. Ooh, I got some good stuff. But anyways, let's continue on. I'd like to talk about some more important information on carbohydrates that I covered on Monday, but I think it's important I cover today, and then we'll do the lab. All right, let me check. That's good. All right, as I mentioned and showed you on Monday, fructose bonds to itself by an acetal linkage to form starch. So you should know if I take an acid catalyst and a lot of glucose, I will make starch. And the key functional group holding starch together, which is a polysaccharide, is an acetal. And that's the key functional group holding glucose together in a starch. And you learn that if you have an acetal or ketal, and you learn this for test number 2, and you add acid and water, you'll get back the ketone or aldehyde you would have used to make that acetal or ketal, plus the alcohol you would have used to make that. So what that means is, if you take starch and add acid and water to it, and give it enough time, like in your stomach, you will make back glucose. And I'm not going to, I can't, spelling before Thanksgiving sometimes fails me, just did. And you'll make a lot of glucose. And that happens in your stomach. And these are all things, let's be subtle because it's Thanksgiving coming up. Right before Thanksgiving, I can't spell. And you should know this. And the other things I'm going to be doing right now, you should know. Now, as I did last Monday, if you take fructose plus glucose, and react it together with an acid catalyst, otherwise known as an enzyme, you will make sucrose, which is what you know as your table sugar. You know, the white stuff you put in your tea, coffee, or in your cereal or cook with. And for the same reason as I mentioned here, the same thing, what holds glucose and fructose together? And that's an acetal functional group, actually acetal ketal. And therefore, for the same reaction I have right here, if I take sucrose and react it with acid and water, like in your stomach, remember your stomach has hydrochloric acid, HCl, and as I mentioned earlier, I think that's one of the miracles of life, that you and I both have cells in our stomach that synthesize, that's a fancy word for make, hydrochloric acid. And therefore, this is the same as the acid hydrolysis of an acetal ketal, and you'll get back fructose plus glucose. Let's see if I can spell it right now. I did. Yay for Dr. White. All right, these are things you should know. Now, one very important or two important things you should know. You should know. Let me make it real evident. Everybody get the message? And know this. You should know how to describe with words and a general reaction what happens when you eat a fat or oil, such as in things that I shouldn't be eating, like French fries, potato chips, or other good things like that. Or if you had a hot dog, or if you put butter on toast for breakfast, you'd be consuming a fat or oil. And what's the functional group in a fat or an oil? And that's an ester. In your stomach, there's acid and water. So how do you describe it with words? That's acid hydrolysis of an ester. And what's the general reaction, which you learned for test 3? Ester, acid, and water. You get back the carboxylic acid you would have used to make that ester, plus the alcohol you would have used to make that ester. And this is the worst looking carbon I've made today. So I'll fix it up. That's better. And you should know how to describe with words what happens when you eat a fat or oil. And that's acid hydrolysis of an ester. You should know how to describe with a general reaction what happens when you eat a fat or oil. And the key functional group we're talking about is the ester and acid and water. You get back the carboxylic acid plus the alcohol you would have used to make that ester. And you should also know, and know this, how do you describe with words and a general reaction when you eat a carbohydrate? What happens in your stomach? And the way to do that, what's the key functional group holding glucose together and the carbohydrates like starch? And that's an acetal. And therefore, in your stomach, there's acid. And because there's water, we call this reaction acid hydrolysis. And the key functional group of an acetal. And what's the reaction, general reaction? Well, acetal or ketal reacting with acid, H plus, water. You get back the ketone or aldehyde. You learned this for test number 2. Plus the alcohol, we don't have to balance it, to make that acetal or ketal. And in glucose, the aldehyde and the alcohol are connected together in the molecule. And you should know how to describe with words in a general reaction what happens when you eat a carbohydrate. And because the key functional group holding glucose together, I like the special effects, glucose together is an acetal functional group, which I showed you on Monday. Because in your stomach there's acid and water, it's acid hydrolysis of an acetal. I'm going to have some water first. Which means in my stomach for my lunch, this is probably happening. because yes, I had some carbohydrates for lunch. And what's happening is acid hydrolysis of an acetal. And you should know how to write the general reaction for that. That's an acetal ketal, acid and water. You get back the aldehyde or ketone plus the alcohol you would have used to make that acetal or ketal. And these are all key things you should know leaving my class and also for test number 4 and the final exam. That's coming up in a couple of weeks. Wow, where did this semester go? All right, guess what time it is? It's lab time. And now I'm sad. Why? Because this is a fun lab to watch the students do. Unfortunately, we're not face to face, so I can't watch you doing it. Shucks. But anyways, today's lab, years ago, as I told you, when I inherited Chem 170 at LG Community College, the labs were awful. Oh, they stunk. Yeah. And I challenged myself. I said, you're industrial, you have been an industrial organic chemist for many decades. You can do better on your own. Part of the problem was the lab at ECC for 170 when I inherited, and it still is, we're face to face. I only have an hour and 50 minutes. When I teach a similar course at another school, the same lab for that course is not an hour and 50, it's 2 hours and 50 minutes. And we can use labs from the lab books that are written. But I couldn't do that at ECC because of the shortened period as opposed to longer lab time. So I challenged myself, and you've been doing those labs all semester. Now, I had one lab left to go that I needed to fill and write. So I had a whole full semester the way I wanted it. And I challenged myself even more. And the challenge was, because I have many, many years experience as an industrial surfactant chemist, how can I come up with a lab that does the following? One, is it fun for students to do? 2, because of the time, and even today it would be the same restraint. It costs almost zero money. You can't buy specialized equipment. 3, it has to do with being a surfactants and surfactant chemist. And finally, how can I give students a real life experience of research? And I came up with the lab, and it's fun. And this is a lab after the semester, if you'd like to, you can do parts of it on your own and have a lot of fun. What's that lab? It's called Developing Competitive Products. And when I was in industry as a senior research and development manager, an R&D manager it's called, I would meet often with the vice president of marketing and sales, or also his senior marketing manager and the senior sales manager. And we'd have a meeting, and I'd be told, we need these new products for our company to make money. And my job and the people who worked for me, their job was come up with new products. And that was my expertise. Well, once in a while, you'd get, I'd go to a meeting like this, and they'd say, you know, our competitor are making this product, and we don't have anything like it. You need to come up with a product like our competitor, because they're making a lot of money, and we would like some of that. And that's called developing competitive products. And that's where you make a product similar to existing product, and you do this by your understanding of functional groups, what's called the patent literature, and the composition of existing products. I won't tell you how we get existing products, but there are ways of doing that, what our competitors using. So in this lab, you're going to develop and test different formulations for a competitive product. And wrong thing, let me get to the right screen. Let me close this. And a competitive product where, let me get this off, you're going to be doing is come up with a competitive product for Super Miracle Bubbles. And as you all know, this is a product, little kids take a wand out, go like that, and blow bubbles. Hold on, let me see if I can find a YouTube. I got people, let's see.
Did you know Google makes a phone? Sure.
Have to wait 15 seconds for the ad. Another ad, I didn't click it fast enough. Sorry about this. Nope, this is not what I want. Hold on. And notice this guy's got a blaster, but see all the bubbles? Let's go back again. See how you can make bubbles? I should have had a. Anyways, you get the message. Sorry, I can't find a good video, but you look for it. You blow, and if we were face to face, I had my bubble solution. And the hardest part to laugh for me is blow some bubbles, but not that hard. And if you look at it, the bubbles come out, and I'm sure you've all blown bubbles when you were a kid. I hope you have. What's a bubble? Well, let's take a look. And don't laugh too hard at my artwork. Let's have a big bubble. And inside the bubble is air. Outside the bubble is air. And I should tell you, air is nonpolar. Oxygen, nitrogen mainly. Now, this part right here of the bubble has water and other chemicals. And you probably don't, but I do. Water is a chemical. And these chemicals are surfactants, also known as soap, with, guess what? Polar head and nonpolar tail. And inside this layer of liquid or water, you form micelles. So different from dirt and soap and water, but here the polar tails wants to be toward the outside air. The polar heads want to be in the water. And this bubble is really one big micelle. So does micelles play a role in this? Of course, because a bubble is this air surrounded by a micelle, surrounded by more air. So this is a bubble. And that's what we're going to be doing today, finding formulations that make good bubbles. Now, in this class, one of the things I know from decades diexperience in research and development is how to set up a grid of experiments, not competitive, DOE, it's called design of experiments, where you have a matrix of different experiments to solve a problem. Now, one of the most important things when you're doing any research, but especially in chemistry, you only change one variable at a time. Water break. And I've seen trained organic chemists who break that rule. And if you solve it, what solved it? If you didn't solve it, what didn't work? You have to only change one variable at a time. And if you look in the patent literature, patents are where you protect an idea so you can just profit from it. I have 10 of them, so I know about that. And that is, you can find about other people what are good ideas, things that they think they want to protect, because a patent costs a lot of money to have a lawyer write up and to file with the government. So if you're going to do that and spend a lot of money, I like my a lot of money symbol, you're going to want to have an idea that will make you a lot of money. And there's a lot of patents on blowing bubbles. Yes, there's a lot of patents on other things too. So what are the key variables? And that is using different surfactants. So in this lab, you're going to be using 3 different surfactants: dishwasher soap, liquid hand soap, and laundry detergent. And certain additives from the patents help make better bubbles. And those additives can be glycerin, corn syrup, and obviously the amount of water you have. And I will provide you the structure, so I better do that now. You should know that your dishwashing soap the key ingredient is this compound. Let me clean this up. And this R group is laureth, which laurel from lauryl alcohol, I believe that's 16 carbons. And notice you have a nonpolar tail and a polar head. This is an oxygen. Now for liquid soap that most of you use, that you can buy at any supermarket, it's similar, but not the same. There are other things in there, but this is the key ingredient. And this is called a sulfate anion, a sulfate ester anion. And here N is usually 3 to 5. So you take lauryl alcohol, you ethoxylate it 3 to 5 moles, then you make it into sulfonate ester. And again, nonpolar tail. And polar head. Now the last one, here's dishwashing soap. You should know the structure of liquid soap. And finally, your detergent, laundry detergent. And whether you use All or Tide or whatever the national brands are, they're similar. They have the same key surfactant. And R here is from 9 to 12 carbons. So you have a nonpolar tail, and a polar head. And what I set up for you to test is a series of experiments. Now, in each experiment, in part A, you'll be making different solutions, and I had to figure it out. Elgin Community College is not going to give me $50,000 for one lab to buy instruments that do certain measurements. So how can we measure bubbles? Simple. When you're a kid, you want it to last a long time. And therefore, what we'll do in this lab, you'll blow bubbles, and from the time it comes out of your wand till it pops, you'll measure the time in seconds. And the longer the bubble lasts, the better type of bubble you can have. Now, when you do this lab face-to-face, at this point, I would be telling you about proper etiquette for bubble blowing. First of all, don't blow bubbles at your instructor. Not good. Second of all, don't blow bubbles at your neighbors who are doing the lab. Not good. And finally, the most important, and this did happen, I had to tell Susan, no, you don't do that in my lab. You don't bust your neighbor's bubbles. Please don't. So you'll measure the time it does. Now, in any experiments, especially in chemistry, you never make one measurement. You don't know, is that real? Is that valid? Is it an outlier, something that just normally wouldn't happen? So for this lab, for each solution, you're going to measure 5 bubbles. Now, you may have to blow more than 5, but you will measure 5 bubbles times, and you'll take an average of those 5 bubbles and record them in your data on the tables. Now, let's look at the tables. In part A, you're going to be testing the dishwashing soap. Now, since it's a liquid, we can measure it by volume. And solution A1, you'll take 2 milliliters of the soap, dishwashing soap, 18 milliliters of water. In A2, we'll double the amount of dishwashing soap. See if how much you have makes a difference in the bubbles. Now, I was read that glycerin helps make better bubbles. Well, does it? So you'll take A2 after you test it, and whatever left, you'll make solution A3, which is A1 plus 5 drops of glycerin. You'll do the same with A4. A4 has more soap, and you'll also add more glycerin. Finally, cornstarch in water, and this should be a solution of cornstarch, which if you were face-to-face, we'd have this all made up for you to test. You've got to make the solutions, but the cornstarch and the soaps and everything are all available. And A5 is you make another A2, high level of soap, and you'll add 10 drops of corn syrup. And what you'll do is start blowing bubbles. Oh, it's so much fun to watch students do this. And because we're not doing this face-to-face, I have taken the liberty to do the data for you. Now, in real life, when you're writing in a lab book in an industry, you write all your results in a lab book, and every week, one of your colleagues, you have to sign and date the bottom of each page, and this is for patent and legal reasons. And someone else in your research group has to countersign that they've read it and date it. In fact, at all companies I've worked at, usually every couple times a year, usually every other month or so, maybe even every third month, lawyers from the company will come through, go into a research group and say to the chemist there, show me your lab books. And if they're not up to date, signed and countersigned, the research manager and the chemist get in trouble. Not fun. And when that happened, the first time I got in trouble for not being up to date, I kept up to date. And then when I became a manager on Friday at 1 p.m., I went to every chemist working for me and said, show me your book. And it better have been up to date, signed and countersigned. And after they learned I was serious about that, they were. And I didn't have any problems with our lawyers either. But when you're doing research, one of the things you always do is test your competitive product, your competitor's product. In this case, if you took the Miracle Super Bubbles, if you did it, you get 10 as the average life of a bubble for 5 tries. Now, here's the data for the different formulations. Now, one of the things I do tell students for this lab, if you try 10 times and can't get at least one bubble, put down 0 for the time of the average time. Because if you can't do it in 10 times, you're not going to get a bubble, good bubble. So that's an important thing. Now, part B, you'll do the same thing. Remember, change one variable at a time, except instead of using the dishwashing soap, which I should mention, we use for this lab here, and I use at home too, we use Dawn dishwashing. And for this next lab, we'll use the liquid hand soap. And at ECC, Dr. Daly, who's done a great job as lab manager there, we use Dial liquid hand soap. At home, I use the stuff I get from Costco, which is quite good too, but at ECC, we use Dial. And here, you're going to do the same test, make mixtures, and then blow bubbles and get an average of 5 bubbles. And here, B1 is similar to A1, except you're using the liquid hand soap. Now, if you've ever used liquid hand soap, it's very thick and viscous, and it's hard to get out of a graduated cylinder. So to make everybody's life easier, by the way, when we actually do this, you do that in small beakers. I hand out wands so students can blow bubbles. And what we do, hold on, my nose itches, excuse me. Time out for a nose itch. Sorry about that. But anyways, instead of measuring it, we'll use weight. And in the beaker, you weigh out 2 grams, add the same amount of water we did before. Then in B2, we will add double the amount and cut back on the water. So you're doubling the amount concentration of the surfactant, in this case, liquid hand soap. And that's B2. B3, like the last one in table A, you take the first solution, in this case B1, and add 5 grams of glycerin. And be careful, here's where my comedy thing gets in. Before what? I can't resist saying that. Sorry. But anyways, take 4B, that way I don't do that joke again, and take all of B2 and add now 10 drops of glycerin and see how that does. And finally, B5, to make another B2 high-level surfactant and add 10 drops of the cornstarch solution. And you measure it. Now, one of the things we do in industry, you don't have to retest it once you've done it once, but when you're doing a competitive product research, you put the benchmark, that's the product you're trying to get as good as or better than, that's what calls benchmark, as good as, on your lab book, on the table you're writing in there. So I did that. You don't have to redo it. But B1, B2, B3, B4, B5, here are the results. And I got these numbers from having done this lab enough years face to face that students get this kind of results. And now we'll do the part C. Part C used the laundry detergent. And my favorite, which Dr. Daly got for me, is all. I've been using that stuff for years. I like it. My parents liked it. But anyways, you'll do the similar thing. Now, laundry detergent is not as viscous, similar to the dishwashing. So we went back to volume, measuring the amount of the detergent. And like A1 and B1, we'll use the certain volume, similar volume or amount of the laundry detergent, 2 milliliters, 18 milliliters of water. Then C2 will double the concentration by adding 2 more and dropping the amount of water, and that's more surfactant. C3, you'll take C1, add glycerin. C4, you'll take C2, add 10 grams of glycerin. Excuse me. And C5, you'll make another C2, add 10 drops of the cornstarch solution, and you'll measure it. Now, remember in the past, or earlier today, I said, if you can't, after 10 tries, get one bubble, put down 0. I can tell you now, but it's fun when I'm walking around. Students will come to me when they do this, say, Dr. White, I can't blow any bubbles with part C or very little. And they usually get all zeros, and they're all upset. And I say to them, what do you use laundry detergent for? And where do you use it? And they all say in their washing machine. And I'll say, where don't you want a lot of bubbles? Also known as foam. And before I do this, I tell a story. I'll tell it after the fact. And I'll say, well, that's why they don't. Now, I didn't put anything in here, but when we do it face-to-face, a couple of years ago, students would come up to me and say, can we make our own formulas? And I said, yeah, that's a good idea. So officially, I put it in. Any of the chemicals we use in this lab here, cornstarch, glycerin, any of the either hand soap, Dawn, or all, they can mix with as much or little water as they want and do their own formulation. Now, and they come up with great formulas. Now, one of the things to make it real, I should mention, one time about 4 years ago, I think it was by now, one student took, in face-to-face, students work in pairs groups, because how many hoods we have in the lab, and their bubble just kept on living to the point where the whole class in the lab, including the instructor, were just standing there watching this bubble float, and it got up near the ceiling, and it lasted over 5 minutes. Yeah, 5 minutes. And it finally knocked into one of the light fixtures in the ceiling, and it popped. And everybody, oh, that's so sad it died, but it lasted 5 minutes. Oh, that was awesome. So this is the part. Now, one of the things I wanted to instill in this lab is real world experience working in a chemistry lab as someone reporting to me or other chemical managers in a research lab. And one of the things I did and others did too is before anybody could issue a report about their research, I had to sign off on it. meaning I had to sign my signature and date it. And before I did that, I'd tell them, show me, because I'm not going to stick my neck out and get it chopped off. And it never happened because I always made sure any major advance before we let the rest of the company know about it, you better show me. And so what I did in this lab is I have students pick their best formulation. You look at your data, you make the choice. I don't care. And then Dr. White has to come over as the manager, which in this lab, I told students, today you're my research group, and the vice president of marketing sales wants this competitive product. We need it. You got to do the research. And I tell the students, to get this lab, you have to blow 2 bubbles each person with your favorite formulation. But when the big boss is watching, it gets interesting and hard. They're under pressure now. It's funny as hell, really funny, but they understand, have a good time. So what I do to have them get that real world experience, here's where they draw. If you were face to face, you blow your 2 bubbles, and then I'd initial it. All right, here's some questions for you to answer. Well, one story I would have told earlier, but I can tell now, is when I worked at this one company, before I got there, they had started it, and when I got there, they were still doing it, and I was part of it. It was all the research managers would go to this local bar, if you want to call it that. It was a real dive, no windows, one long bar, and some tables. And we'd have on Friday after work, we'd have a couple of pitchers of beer to end the week, complain about our employees, complain about upper management, blow off some steam, talk about things. And it was a nice way to end the week. Well, we had this bar, the owner had a talent, and that was in a pitcher of beer, he could make a third of it foam. So you're getting ripped off. And if you complained about it, and one chemist did, one manager did, he told them, well, go elsewhere. Not a friendly guy, the owner. So it turned out, and I wish it was me, but it wasn't. One of the other managers was getting really mad. And he knew surfactants like I did. And there are different types of surfactants. It turns out a surfactant, which you're doing in this lab, can make bubbles. There are also surfactants that stop bubbles from being made. And it turns out a couple years earlier, when I had a serious problem with a waste treatment pond that I had to solve, if I didn't in a couple of days, I had to get this special type of foamer to stop from a waste treatment of foam going on to, 47th Street in Chicago. If that had happened, we would have been fined a couple $1 million. I actually had 4 drums of this surfactant. It's called, since it stops foam, a defoamer, flown from overnight from California to Chicago. Boy, that was expensive. And that was always on that flight, but it saved us millions of dollars, so it wasn't that expensive. Well, what you don't know is all chemical companies, or any company that sells chemicals, and chemical companies and their distributors, but chemical companies have what's called a sample room. And a sample room is where you have all your products, and I've managed one along with other things at one company. Not a fun job, but it's an important job, that if a salesman has a customer who's thinking, or a potential customer, I'd like to buy your chemical. Well, let me send you a sample and you can experiment and see if it works for you. And samples can be anywhere from 4 ounces up to 5-gallon buckets. And depending how big a customer you are, important, and it's free. Well, this, in a sample room, when we're talking about chemical industry, there are 2 types of chemicals: industrial chemicals and food grade chemicals. Industrial chemicals are high purity, but never to be consumed. Food grade are high purity chemically, but also, and here you can tell I'm a chemist, not a biologist, biologically pure. In other words, here's real scientific term, yuckies in there to get you sick. It's biologically pure, whatever that means. So this chemist, without telling anybody or manager, because he was upset with the foam in the beer pitchers, got some food grade defoamer, got a little squeeze bottle. This stuff is powerful stuff. Remember, I used 4 drums. A drum is 55 gallons. So that's about 220 gallons to take care of a waste treatment plant that I think I calculated had about 10 million gallons of liquid in their water and waste. So this is powerful stuff. So he had this little squeeze bottle in his coat pocket. And when the owner wasn't looking and we were almost done with the pitcher, he said, shh, don't tell anybody. Took it out, put a few drops in, swirled around. We need a new pitcher. If you've ever been in a lot of bars, they'll have a sink with soap and water for a pitcher, and then 1 or 2 rinse sinks. Well, after our second or third pitcher, the soap sink and the rinse sinks were contaminated with the defoamer. And the owner of this bar was getting really mad because he no longer could put a head on a pitcher. And it cost him more money, so to speak. He was really cheating the customers, but let's not get into that. And we started laughing. We stayed longer that night and had a few more pitchers. And finally, he realized, you guys are scientists. I know that. What'd you do? Oh, we didn't do anything. And we're laughing. It's safe, nothing wrong, dangerous. And he said, get out of here and don't come back. And we did. And we found another bar that gave us fuller pitchers. But I would tell that story before he did the lab. And some students would figure out, guess what? Laundry detergent has a defoamer. Now, liquid hand soap and Dawn has a foamer in it, and they're designed with the surfactant to make foam. Guess what? The foam doesn't do anything to help clean things. It just looks good and you've been trained. That helps. What really matters is, as you've learned, making micelles to clean things. But for this, it's you learned about laundry detergent. Now, one final thing. I have, over the years, when I've taught this a number of times, that students will tell me after I tell them about the all, say, oh, I did, or a friend did, ran out of laundry detergent and put Dawn in there. Guess what happened? The whole area was flooded with foam. You don't want foam in a dishwasher. Or another one, somebody did laundry detergent, a washing machine. And another time they told me about how someone put Dawn in their dishwasher machine, and that just foam came everywhere. Anyways, on that happy note, I'm done for today. Have a happy Thanksgiving. Don't forget tonight, no office hour. And with that, I'll say happy Thanksgiving again. Gehen gesund. Goodbye.